And welcome back. Now on my workbench today we have a standard Uno, forgive me for laughing, and yes, the flashing LED. Now I can almost hear the groans from here that you're thinking, not another flashing LED, is there nothing else we can show? But sometimes simple is best. Yeah, keep it simple, stupid, and believe me, I'm as stupid as they come. So flashing LED today is in fact one of the simplest ways of showing you how to link in a little tiny assembler routine into your main sketch. Why am I doing this? Well, it's all part of that AVR GCC compiler optimization video that we did, when was it, 2-3 weeks ago? And yeah, there were some comments there about, you know, assembler and all that. And I thought, well, yeah, I suppose we could do a little tiny demo just to show how easy it was. Of course, if you don't know assembler, some of the constructs might look a little bit odd, but frankly, I've laid it out a bit like a program, so I think everybody will be able to follow this. Look, you there, you're a beginner, right? Yeah, it's you. You admit you're a beginner to Arduino. Follow this. This is all right, actually. A beginner will be able to follow this, no trouble at all. And whilst I'm not expecting anybody to write a bit of assembler to flash an LED when we have a perfectly good blink sketch available, it's good to know these things, and things stick, don't they? And in the future months and years you think, oh yes, there is a way of doing this. Okay, before we move on, let's have a quick word from our sponsor. I'd like to give a big shout out to my sponsor, PCB Way, PCB Prototype the easy way. Let's have a look at their new Superior A+ Advanced PCB. Here you can find all the details of what their advanced PCB service consists of, and there's a handy comparison table to see the benefits of the advanced PCB service. Scroll down to the PCB showcase and you can see some examples of what they can do for you. Just go to their easy online PCB instant quote page and select the advanced PCB option. Simple. If you have advanced requirements for your PCB, try PCB Way. Try them now. Excellent stuff. Now, just before we actually move on with the actual demo today, as you can see on my workbench, there's this ePaper screen, yeah, and it's been sitting like this, unpowered, for, well, I guess a week now, and it's still okay, and the white hasn't gone too pink either. In fact, I'm not sure it's gone pink at all, quite frankly, which is one of the caveats, wasn't it, on that Adafruit page, saying if you don't refresh it once a day, this whiteness could end up rather pink, but don't think it's happened. Anyway, yeah. So now I can disconnect all this. I just wanted to show you that first. Yeah. What video was that? Come on, pay attention, guys. It's that one from a couple of weeks ago. Yeah, that one there, look. They are quite interesting. I still haven't got a use for that screen, though. No, never mind. Okay, right, let's move on with today's demo then. How do we call a little assembler routine to flash an LED and perhaps update a counter within a standard Arduino sketch? Okay, this is all about code. Yeah, I'm sorry. Yeah, some of you are thinking, oh no, not more code. But hey, you got 2 flashing LEDs to look at, haven't you? In fact, 3, because the TX LED on here also flashes because we're sending stuff out via the USB UART, aren't we? Great. Okay, let's have a look at the code. Right, first things first, the Arduino sketch itself. Okay, now I've collapsed all the comments down in this sketch because believe me, I've commented it to death, quite frankly. There's more comments than anything else. So I've collapse all those down just so you can see the bare of what we're all about. So what we're doing up here is declaring a volatile uint16t. You what you say? Look, that's just the official way of describing an integer. When I say integer, how do we know how many bytes that takes up? Well, all right, by experience you might know that it's 2 bytes, but on other platforms it could in fact be 4 bytes. By saying integer, it's all a bit unclear, isn't it? Friendly, admittedly, from an Arduino point of view, but unclear. So what we're saying here, this is an unsigned, that's what the U stands for. It's an integer of 16 bits, 2 bytes, underscore T, a type. That's the type that's been declared here, right? And we're calling it my counter. So all we're saying here basically is int my counter. Great, we've all done that. Volatile is telling the compiler, look compiler, I know you think you know best, and yes, most of the time you do. No, I'm talking to the compiler, not my wife. And so we're telling the compiler, you know best most of the time, but occasionally you need a little hint. And what I'm telling you is, even though you might have read the value of my counter now and you've put it into one of your working storage variables that we know as a register, you can't use that, I'm afraid, because we're updating the memory behind that register. So you've always got to go back to the actual memory location in SRAM and retrieve it again, even if you don't think you have to. So the compiler will now say, ah, I see, it's an unsafe value I have in my register because you might have updated it in the background. Exactly. And we do this a lot, of course. Well, we do this all the time when we write interrupt service routines, ISRs, timer stuff, yeah, watchdog stuff. Anything that's updated by an interrupt, rotary encounter, another example, has got to be declared volatile so that the compiler is forced to go and retrieve it from memory, not rely on a value that it's previously retrieved into a register. Okay, great. Okay, we've all done that before. Now the next bit I just put in because I could really. I'm saying in our sketch we're going to call this my counter. It's a good enough name, you know. But within my assembler, as in ASM, assembler, that's what it's short for, we're going to call it counter, just because we can. Now, if we didn't put that in there, it would probably be called my counter, but assembler has a propensity to mangle names if you're not careful. So by saying I'm calling this counter in the assembler routine, it just makes it crystal clear what we're naming stuff, okay? And then we're putting on this attribute here. Now this attribute, that's underscore underscore attribute underscore underscore. Yeah, I know. What we're saying here is, compiler, again, I know you might think this particular variable is not really used anywhere in this sketch, but I'm telling you it is being used. So please do not optimize it away, and it will optimize it away even with the standard settings that the Arduino guys have set up. Remember, dash capital O S for size. Yeah, it will say what the compiler would normally say if we didn't put this on there. It goes, you've declared a volatile integer, my counter, and you've set the default value to 0, and then you've not used it anywhere in this sketch. All you're doing at the end of the day, if we scroll down to the end, is say we're printing it out. Well, the compiler, being a bit clever, says, well, you've not done anything with it and you declared it as 0, so I'm going to remove that entire line as though you never wrote it and just put 0 in there instead. Not what we want. So by saying, excuse me, compiler, yes, I know you know best most of the time, but here we're telling you we are using that value. Do not take it away. Don't think you're going to optimize my code by removing that, because you're not. You'll stop it working, okay? So that's what that whole big long sentence says. Okay, so it's volatile. You've got to retrieve it from memory. We're calling it uint16 underscore t. Yes, I could have put int in there, but this makes it very specific. We're calling it in this sketch my counter. But within the assembler routine, which we'll come on to in a second, we're going to be calling it counter. It sort of ties the two together and makes sure that the symbolic name is being used rather than the variable name. We'll come on to that. And the attribute used means we are definitely using this. Do not optimize it away. Cool. That's quite a lot, isn't it, for one sentence? But, you know, these things are necessary. And then what we're saying is, now compiler, listen up. I've got two external C routines, well, C compatible routines, and one of them's called start and one of them's called blink. Okay, so just take that at face value. I've got them somewhere. The linker will find them eventually. So when we come and call them in our standard Arduino setup routine here and say start, the compiler doesn't throw a wobbly and go, what's that all about? No, we've already told you, look, there's an external file somewhere with that program in, that routine in, assume it's there. Okay, so the compiler says, okay, you've told me it's there, I'll put a call into it, let's hope the linker finds it. And in the loop, when we call blink, it will also find this external, I keep wanting to say the word sketch, it's not, it's an external program, assembler program, called blink, and it says, okay, I'll assume that it's there, I'll put in the right code for it, we better make sure it finds it. And if it doesn't find it, you'll get an error in compilation. Okay, so then we're putting out a quick serial statement saying that's a blink, and then we're outputting that counter that we declared right at the top of the sketch. which we hope by now has been updated by the background running of the assembler routine. So as you can see in here, there's very little code. Okay, this could almost be a Blink program if it were not for these external routines here doing the actual donkey work. Right, now if I expand that all with the comments, you'll see that there's more comments than anything else, right? And it explains pretty much what I've just said, why we're doing things. Yeah, everything that I've said, I hope, is now in the comments. So that's it, all done and dusted. Well, that's the sketch bit that's all done and dusted. Better talk about assembler now then, hadn't we? Okay, on to the assembler program. Now, before you all throw a wobbly and go, I'm not learning assembler as well as C++ and all the rest of it, I'm not expecting you to. I'm just showing how you might link into an assembler program that maybe has been written by somebody else, a third party perhaps. Yeah, this happens all the time in the commercial world. And in this example, if we go back to the actual sketch, what we're going to assume for this particular sketch is that we need a blink of an LED to be very precise. We're going to say, I want to be able to control the blink of LED every second, and it's got to be every second, not nearly every second. And we'll assume, for the purposes of this demo, we don't have things like timers running, and we don't have things like millis running, yeah, that would enable us to do it in a blink of an eyelid. No pun intended. Well, there was really, but we're going to assume we haven't got any of those features, so we need something that's very specific. And the way we can do that in the assembler world is to say, right, if I write all these instructions to turn a pin on, digital pin 13 in this case, and wait for a bit, and then turn it off and wait for a bit, and just keep doing that forever, we know how long each one of those instructions take, as in how many clock cycles. This Arduino is running at 16 million cycles a second, right? Because that's what that big fat chip on there, that crystal is doing there, right? 16 megahertz. Now, that's a lot to get your brain around, actually. I mean, we blithely say, oh yeah, this is running at 16 meg or 20 meg or whatever. The point is, the Arduino is running at 16 meg a second. A second. And lots of instructions in the assembler world only take one cycle. Some take 2, some take 4. But, you know, it's still a lot of instructions you can output in that tiny blip of one cycle, isn't it? 1/16 millionth of a second. Okay, back to the code then. Right, let's just flip over to the assembler then. Now, when you write assembler program, you can call it anything you like, but put it in the same folder as your Arduino Sketch and put on the end of it, instead of .ino, capital S. Must be a capital S, right, for the compiler to find it and compile the code. Right, here we go. So this is it. Now, there's more comments in here than code, and I'm not going to describe every single tiny bit of this code. I've described it in the comments already. I'm really not expecting you guys to start suddenly writing assembler. I mean, I only did it as an example. I used to write pick assembler many years ago, and it was so much hard work. And when I found a really good compiler that wrote, it wasn't in C, it was in BASIC, but it produced really nice tight code. I was just so happy, because assembler is just so long-winded and it's easy to make mistakes. And anyway, enough of that. First of all, okay, let's just whiz through then the lines, right? We have to say the special function register has an offset of 0 because of the way Arduino have set up all their functions and stuff, and if you didn't put that in, it'll just fall apart. But just skim over that, I think, really. Now, because we want some friendly names like port D and DDRB and all this, we have to put this library in where they're all defined. Otherwise, if you didn't put that in, the assembler compiler would go, what the hell is port D? I've never heard of it. That's not an assembly instruction. But by doing this, they're defined in there as a particular special function register. Okay, we'll sort of skim over that a little bit as well, really, just to say friendly names are all in there. Now, we referred to start and blink as routines, didn't we, in our sketch. These ones here have to be accessible to this sketch in order for it to work. So what we're saying over in the assembler routine is, look, these are global, all right? Otherwise it would not find them. So what does the start function that we've both declared in the Arduino Sketch and written here, what does it do? Well, basically, as the comment says, it sets PB5, you what? What's PB5? Digital pin 13 to you and me. It sets it as an output pin, all right? And then returns. RET is short for return. So if you really want to know what SBI and all that stands for, it's set bit immediate data direction register for port B, bit 5. What? Yeah, that's it. It puts a 1 on that bit. Now, if you go back to the compiler optimization from that video we did 2-3 weeks ago, you'll see that I did exactly the same with a binary value. Yeah, so bit 5 of that data direction for port B got a 1 in it, and that made it an output pin. And that's it. That's all it does. Pretty quick. So that's the first thing we're calling. And that just works. What about the blink then? Well, the blink is, as it says, a bit like a loop. I mean, that might have been a bit of preamble, but like a setup. This is more like the loop. So what we're saying here is set pin 13, which is port B, bit 5, high. So basically it goes high, the LED goes on, and then these two lines here, they're the thing that call a little routine that delay things. All right, and I'll try to make that accurate, but we'll see how well I did. Then we say clear that bit, CBI, clear that bit immediate on port B, bit 5, which means bring it low. Fine. LED goes off. Marvelous. And then we'll delay a little bit more. Okay. Now, as well as all this flashy LED stuff, which yeah, I know, it's the best I could think of. All right. What we're also going to do is update that volatile integer that we declared in our sketch, right at the top of the sketch. Remember, right up here? Here it is. Yeah, this one here, that we're calling my counter in the Arduino sketch, but which we are going to call counter, or somebody else has determined that it's called counter in that assembly routine. So what we're saying here is, I want to update that counter, please. And the way you do that in assembler, because it's an integer and it's in a most significant byte and a least significant byte. Obviously, there's 2 bytes that make up an integer. We basically copy the value into a special register pair within the assembler routine that's designed to hold an integer, and then we add 1 to it here. In fact, I'm adding 2 to it because I've been playing about just to see what, how far I can go with this without getting everything totally confused. So we're adding 2, as you can see here, the hex for 2, to one of the registers, which is the lower register of the register pair, and we're saying add 1 immediately to the word. Now, word in this context means 2 bytes. Right? That's what an integer takes, a whole word of 2 bytes. That's standard for everything in AVR, really. Okay, so having added 1 to it, we then copy the value back into counter, and this is how you do it, right? We store it back into counter, low byte, high byte, the end, and then we return. So what we've done, we've set the digital pin high, we've waited for a bit, we've set the pin low, so the LED goes off, we've added 1 to the counter, 2 to the counter, and then we've returned. Job done. It's going to flash, isn't it? And you saw that at the beginning. We can have a quick look at the delay that I've done here. Now, I tried to get the delay spot on. Unfortunately, a partial success, a bit like a curate's egg. Excellent in parts, but as a whole, it doesn't totally work. I'm going to let you read this in your own time, frankly, because it's all documented to the nth degree. And as I said at the beginning of this sketch, we know how long each individual instruction takes. Therefore, we know how long we've got to go around in a little loop, how many thousands of times for it to take a particular length of time. Now, this delay, as the title says, was designed to delay for 10 milliseconds, right? And I worked out that if we went round a certain loop through 39,998 times, which is this inner loop here, it whizzes round here, and then does that however many times you want. So if you just wanted a 10 millisecond delay, you just do it once, because we want, say, a 500 millisecond delay, yeah, or 100 milliseconds, and then a 250 milliseconds, whatever. We run round the inner loop that many times, just as you would in the blink statement, to slow the whole thing down. And then when it's all done and dusted, there's a no op here, no op, which just does nothing for one clock cycle, just to bring the total count of clock cycles that we've now used up. Very wasteful, isn't it? This very wasteful. And then we return. And that's it. That's the delay. So the return here returns to where it is called from. So if we scroll back up, so where we call here the delay, whoops, that one there, our call, and here it returns to the next statement after this, which, so from here it'll obviously go to there, and from here it goes down to here. Right. Now I've documented all this to the nth degree as well, just so that if anybody is interested, you can follow it through. Of course, if you're going to write assembler, you'll need to know all the operands and stuff, and that is a skill in itself, and I'm certainly not skilled in that. These are just a few relatively simple commands that I've cobbled together just to prove the point. But you could, of course, make it as complicated as you want. Just imagine the poor people at Arduino who have had to write all the stuff pretty much from scratch, really. I mean, it's quite a task, isn't it? So that's it. Anyway, and the point of the delay is that it took a certain amount of time to do that. And as the comment at the bottom here says, if you do it once, it takes exactly 10 milliseconds. Ooh, got it right. Unfortunately, if you'd call it 10 times for 100 milliseconds or 50 times for 500, little errors start creeping in because there's one less clock cycle used when you do it this many times, and slowly it builds up. It just doesn't matter. Not for this, all right? What it does allow you to do, of course, because I said you can do that in a loop of 10 milliseconds however many times you want, what we've done here in the main program, the main blink program, is to say, right, I want to do it 10 times initially, so 10 times 10 milliseconds is 100 milliseconds, so that's how long the LED is going to be on for. And then in the bit after we've turned it off, we say, well, I want to do it 90 times. So 90 times 10 is 900 milliseconds, 0.9 of a second. So overall, the whole thing on and off takes 1 second. Let's have a look at that flashy again, shall we? Here it goes. Now, is that 1 second? You reckon? How are we ever going to know? Well, you're not really, unless you put some other code into the sketch, the standard Arduino sketch, to say it took this long. I thought of doing that, but I thought it's just going to complicate matters. Now, we do output in the main Arduino sketch, and we said, now print my counter. So there should be something coming out on the debug window. So let's have a look. Let me fire up the debug window and we'll have a look. Okay, so we're connected. There we are, setup complete. And as you see, it's going up in 2, because that's what the assembler program behind the scenes is now adding up. Yeah, I know I was playing around. It should have been 1. But it doesn't matter in the slightest, does it? It's just a demo, right? So we can see now that from within the sketch of the Arduino, where we've declared this volatile integer that we're calling myCounter, and we're doing a serial.print myCounter, the assembly routine is calling it counter, adding 1 to it, and it's all tying up. Right, the same bit of memory is being used both in the Arduino sketch and in the assembler, and the two are talking to each other, if you like. So we're not duplicating the storage, it's one storage for that variable, that 2-byte integer. And I felt it was quite important to show that you can send stuff backwards and forwards from the assembler to the Arduino sketch, and indeed vice versa. So if we'd initialize this here in our sketch 10, say, that would work as well. Sorry, you want to see that working. Okay, let me change it and we'll compile it. You'll see some stuff down here, and this will change. Let's do that now. Why not? Live. Right, so let's put a 1 in there. So we're starting now counting from 10. And while we're at it then, where we count up in 2s here, so we're counting 2, look, let's make that 3. Why not? Yeah. So we're going to compile. Now this will work in the standard Arduino IDE just the same. This is obviously not the Arduino IDE, but it's pretty much the same. So we can compile and look down here and you'll see some messages. There it goes, blah de blah. It's the linker working and 0 errors, 0 warnings, which quite frankly we'd expect. Let's upload that into the Arduino itself. It's asking me, you can't see this little pop-up, do you want to build? No, we've just done it, thank you very much. So just get on and do it. And we'll see this bit over here change. It will go back to, there we are, setup completed. Oh look, 13, 16, 19. So we started from 10, added 3 straight away. So I went to 13 and it's going up in 3s now. Marvellous. Okay, so I think we've proven then in this video, yes, with a few simple lines, we can call assembler routines, no trouble at all, and it works, and it updates a shared memory location of, in this case, an integer, but there's no reason to suppose that, a string wouldn't work. And of course, simple 1-byte characters are much easier to address, but I mean, I think using an integer in this case was probably more useful. So there we are, that's it. And I think basically this is going to call a halt now to me trying to get down to the nitty-gritty of Arduino code. I think I've covered all the things like port D and DDRB and using now assembler as well. I think we've done it. Well, I hope this was interesting, if nothing else. As I say, I don't expect any of you to write this, but I will put these 2 sketches up on the GitHub so you can download them, put them both into the same folder, compile them, and you'll get what I'm getting here. And then you can go into the, well, mainly the assembler one really, and you can change the delay by uploading or changing the value that we're putting into register 20 in the both of these things. So this is the on time here, and this is the off time, the 90. And remember, they're multiples of milliseconds. And you can also change how much you're adding to that counter here. Yeah, as I say, we're now adding, as you can see over here, 3. And of course, the fact that this has now scrolled well past 255, and it's carried over the value from that 1 byte that it was updating into the next one, i.e. the word, proves that that worked as well. Cool. Right, next week we'll do something completely different, to borrow the words of Monty Python. Great, thanks very much for watching. Look forward to seeing your comments down below. See you in the next video. I hope you're finding these videos useful and interesting. There are plenty more videos to choose, and a couple are shown below. And if you'd like to subscribe to this channel, just click on my picture below and enjoy the rest of the videos. Thanks for watching.